Swayam Prabha. Digital India. Educated India.
We're going to discuss how the stress vector on an arbitrary surface can be written in terms of stress vector on standard surfaces, okay, by using the principle of stress equilibrium. So, that is the idea. So, that is the objective today. What I want to talk about a little bit is, supposing you have an integral of f of x dx from, let us say, a to a plus epsilon. So, this is a one dimensional integral, okay, and because this interval of integration is very small, I can write it as f of x, the average value of f of x multiplied by epsilon, the length of the interval, okay. So, if you remember, the area under the curve is your integral, okay. Supposing you have a function f of x, okay, and this is a and this is a plus epsilon, this area under the curve is your integral, okay. So, this is the area under the curve. If the distance is very small, then the changes in f are not going to be significant, and I make a good approximation by taking the average. So, I have just drawn it big for you to see it, but actually if epsilon is very small, I can just take the average value between a, from a to a plus epsilon multiplied by epsilon, that will give you the area of the rectangle, and that is an approximation of the area under the curve. Okay, we are going to use this later on in whatever we are going to see today, okay. So, yeah, curve, and this is approximated by a rectangle of height average of f of x in that interval a to a multiplied by epsilon, okay. Now, what I want to do is go to the stress equilibrium principle over the control surface. This must be equal to 0. This is what we said, okay. This is true as long as your control volume is very small and includes the point x over which we have interest. So, in order to be a bit more specific, what I am going to do is take my control volume as a tetrahedron x3, okay. This is A, B and C, and this is origin O. So, I have this 3-dimensional space in which I am considering a tetrahedron. Tetrahedron has 4 faces. One of these is the inclined face ABC, and what are the other faces? They correspond to the x1 x2 plane, x1 x3 plane, x2 x3 plane, okay, passing through 0, passing through O. So, this one OBC is one face, AOC is one, AOB is another, and ABC is another. There are 4 faces, okay. So, this is, and you can understand what I am trying to get at, x is some point in between inside, and this is a very small tetrahedron. I am going to apply the principle of stress equilibrium on this control volume, on this control surface, okay. So, basically integral, apply the principle of stress equilibrium, and the way I have drawn the axis, the unit vector which is perpendicular to ABC is n, okay. The vector which is perpendicular to OBC, outward normal, is in the direction of minus E2, x2 is in that direction. So, this particular OBC has an outward normal in the direction of minus E2, okay. Outward normal of OBC is in the direction minus E2. Outward normal of OAB is minus E1, and outward normal of the other one, which is OAC, okay, is minus E3. And what about ABC? Outward normal of ABC is n, because it is some arbitrary thing. What I want to show is that the stress vector acting on ABC actually depends upon n, the surface, that is the idea, okay. So, if I want to apply the principle of stress equilibrium over the entire control surface, I have to look at all these 4 faces, all these 4 parts of my control surface, okay. These are the 4 parts, okay. So, integral T dA, because this is very small, I am going to write this as integral T of n, the average of T of n, dAn. What is dAn? It is the area of the inclined plane ABC, okay. This is a surface integral, remember, this is area of ABC plus average of all the other why am I taking average? Because it is a very small control surface. I can like I told you earlier here, interval is small, I can represent it by the average multiplied by the domain of integration, okay. So, average of the stress vector multiplied by the area over which I am integrating. Now, what is the next one? The next one is average of T minus E1 delta A1 plus average over T minus E2 delta A2 plus average of T minus E3 delta A3. So, there are basically 4 contributions, okay, from the 4 parts of the control surface, and I have just enumerated them. This basically tells you the direction of the outward normal, okay. So, this is T of minus E1 multiplied by delta A1, the area over which it is acting. So, this is E2, this will be E1, okay, minus E1, this is minus E2, and then this is minus E3, you understand. Minus E3 is acting, N is on ABC, minus E3 is on OAC, okay. So, this is basically the has to be 0 from my principle of stress equilibrium. The force is acting on that particular area, the average multiplied by dN plus this must be 0. Now, from Newton's third law, we can write T of minus E1 as minus of T of E1, because there is a so T of minus E1 must be equal to minus of T of E1. So, if there is a force acting in a particular direction, okay, on this in the negative direction, what is going to be the corresponding force in the positive direction? It is going to be the negative of that. Okay. So, basically that is what I am saying. T of minus E1 is minus of T of E1, which means I can write all of this as with a negative sign. Okay. So, average of T of n, did I write DAN? Yeah, DAN equals average of T of E1 yeah, times dA1 plus average of T of E2 times dA2 plus average of T of E3 times dA3. Now, what is dA1? dA1 is nothing but where is E1 here? Maybe, yeah, dA1 is this OAB, okay, where the outward normal is minus E1. This is nothing but the projection of this inclined surface on the x2 x3 plane. Okay. So, dA1 is the projection of the ABC or DAN in the x2 x3 plane. Okay. So, basically since you are talking about projections, you remember that when you take dot products, you basically are getting a projection. Okay. So, I can write dA1 as n dot E1 DAN. So, dA1 is nothing but the projection of DAN, okay, on this plane here. So, when I am projecting it, I project the outward normal, the vector here is in the n direction, the outward normal here is in the minus E1 direction. So, that is basically what it is. Okay. So, I can do the same thing for others. So, dAI is n dot EI DAN. Okay. Now, I am going to substitute for all the dA1, dA2, dA3 in terms of DAN here. What do I get? Equals DAN is n dot EI average of T of EI DAN. Okay. I really should use some summation funda here. So, let me do that, no. Or let it be as it is. Oh, why am I doing EI? I'm going to do it. I'm writing it for all the three terms. Okay. I'm writing it for all the three terms. Yeah, DAN. Yeah. This is multiplied by DAN plus n dot E3 average of T of E3 DAN. What have I done? I have taken the dA1 here, I have written it as n dot E1 DAN. I have taken the dA2 here, written it as n dot E2 DAN. E3 is dA3 is n dot E3 DAN, the projection. So, now I have DAN common everywhere, okay, and that is the reason I did not want to do the summation thing here, because we are not summing, and I can cancel out dn because dn is not 0, I mean it is a non-zero quantity, okay, and it is tending to 0, but it is not 0. So, I am cancelling it off, and what I am left with is I can write average of T of n equals n dot E1 T of E1 plus E2, and it is all average, T of E2 plus E3 So, basically I have taken out the n dot common and I am writing it like this. I want you to understand that E1, E2, E3 are vectors and T is the force vector, a stress vector acting on the surface. So, this also has 3 components, stress vector also has 3 components, okay. This is a vector. So, EI are the unit vectors, okay. For example, E1 is 1 0 0, E2 will be 0 1 0, okay, and T of E1 is going to be also has 3 components, and I am going to write it as T11 E1 plus T12 E2 plus T13 E3. The first subscript T1 represents the outward normal, okay, of the area that we are looking at. So, this is dA1, what is the direction of the outward normal? T1, that is the first subscript. The second subscript tells me the direction of the stress vector or the force. Remember, on this surface we have a force acting. This force is also has 3 components, x, y, z. There will be an x component, there will be a y component, or z component, or component in one direction, component 2, component 3, because x, y, z are now 1, 2, 3, okay. So, this guy, the second subscript tells you the direction of the force. This is an arbitrary force, T of E1 can be arbitrary, I do not know what the direction is, and I am specifying 2 subscripts. First subscript is telling you the direction of the normal, second subscript is telling you the direction of the force, okay. Is this clear? So, when I said Tij is the force per unit area acting on a surface whose normal is in direction I and the direction of the force is J. This is also a vector, this is also a vector, both of these are vectors. Now, what I want to do is, so when I am taking the average, I am not trying to talk, I am not talking about the magnitude, I am retaining the average of each component, okay. Now, since this is a vector and this is a vector, this is basically your dyadic product, which we saw earlier. When we talked about the rho v v term, the 2 vectors v v, okay, and you got 9 elements. So, this is all of these are dyadic products, okay. And what is done is, before I will explain in detail, this is written as n dot t, and this is called the stress tensor. Now, how does one calculate this stress tensor? So, basically you can see I have n dot t here. So, I now have some hope of converting the area integral to the volume integral, because whenever I had integral n dot dA, I use the Gauss divergence theorem, okay. So, basically we are already there, but I want to explain how what is this T. So, take E1 T1, T of E1, okay. How do you calculate E1 T of E1? So, this is, let us forget all this average right now, E1 T of E1, okay, because very small, average is the same as the value there at the local point. E1 is the vector 1 0 0, and T of E1 I told you is T11 E1, I mean T11 plus unit direction plus T12 E2 plus T13 E3. I will go slow, okay. I want to now use the matrix formulation to understand what is E1 T E1. Can you try doing that? Because I need to get a matrix, right, because I told you this is a dyadic product. So, you should get a matrix, and the best way to get a matrix is, I am going to write this as a 3 by 1 vector. I will write this as a 1 by 3 vector, okay, 3 rows 1 column, 1 row 3 columns, and take the product. So, that is what we did when I said you can also look at a dyadic product in the form of a matrix. So, I am going to write this as 3 rows 1 column 1 0 0, and the other 3 columns will be T11, T12, T13. This is E1 T of E1. E1 is the unit vector 1 0 0, because the first thing, and then T of E1 will be, because acting on the first surface, okay, the first subscript tells me T1, second subscript tells me the direction. I am writing this also as a row vector. So, clearly this is 3 by 1 and this is 1 by 3. When I multiply it, I should get a 3 by 3 matrix, okay. And what will be this 3 by 3 matrix? It will have T11, T12, T13 and 0 everywhere else. Okay, all I have done is matrix multiplication. I am telling you how to evaluate this term here, E1 T of E1. Similarly, E2 T of E2, what will that be? That will be 0 1 0, and that is E2. And what is T of E2? The elements will be T21, T22, T23. The first subscript tells me the direction of the normal, okay, and the second subscript this tells me direction of the normal, and second subscript tells me the direction of the force. So, on this surface, the first subscript is this, but on this surface I can have all three components of the force. I will have a force in this component, force in this direction, force on this direction, okay, 1, 2 and 3. So, the first subscript tells me T1, T11 will be the normal component, T12 will be a tangential component, T13 will be the other tangential component. So, on this surface there is one normal direction, two tangential directions, okay. So, that is basically what I am trying to write here. And if you want to do this matrix multiplication, you will get T21, T23, T22, T23, 0, 0, 0, okay. And similarly E3 TE3 will be 0, 0, 0, 0, 0, 0, T31, T32, T33. Okay. So, when you add all of them, when you add these three things on the right hand side, you are getting T of n is n dot this tensor T, which is n dotted with T11, T12, T13, T21, T22, T23, T31, T32, T33. Okay. I am going too fast? One way to slow me down is to ask a question, okay. I do not have a problem in repeating what I have said. So, okay, let us just recap a bit. I started with the principle of stress equilibrium, okay, and I am just telling you the net forces acting on the control surface are going to be 0, and I chose a particular control surface enclosing a control volume with 4 faces. One was arbitrary, okay, and the other 3 are not arbitrary, they are standard, because the outward normal is in the direction of 1, 2, 3. What have we done so far? We are saying that if you have an arbitrary surface, you know the direction of the normal, okay, to that surface at a particular point, you can write the stress component in terms of the classical 3 directions E1, E2, E3. That is what we have done. So, if given any arbitrary surface, I can write the stress vector acting on that particular surface in terms of stress vectors acting on the 3 surfaces whose outward normals are in the E1, E2, E3, because E1, E2, E3 is standard. Otherwise, every time you have to worry about how to do the calculation of the stress vector, okay. So, all you have to do is calculate the stress vector on 3 surfaces, which are the standard surfaces in the one direction outward normal, the second direction outward normal, third direction, that can be done. And if I tell you some surface with an outward normal, you can use this method to calculate, okay. So, that is the whole idea. So, this is what this whole thing is. So, and in the process what we have done is the stress vector T of n, I have written it as n dot T, okay, and now that helps me convert the area integral into a volume integral, because now I can write the volume integral as divergence of capital T, the stress tensor. So, T, remember, I want you to understand, this is a vector, okay, this, and the 3 components of this vector are the forces components acting on a plane whose outward normal is in n. N is the outward normal, T is a tensor. So, this has two things you have to specify. So, when you write this in the form of your ij notation and you take the dot product, you will get a vector. So, everything is fine. It is not at the end of the day, a vector must be equal to a vector. Okay, you can't have a vector equal to a scalar. Okay. So, I mean these are cross checks you have to make. What I am trying to tell you is, and T is a tensor, I do not think I need this. N dot T, this is a vector, this is a tensor, and this is written as NIEI, right, the components, and T is written as T JK EJ EK, and you take the dot product, you get Ni T J K I is equal to J, I equal to J, so I will write this as T I K E K. Is this clear? Whatever we did earlier, when you take a dot product, the two unit vectors which are adjacent to the dot is what you are looking at, EI and EJ, I must be equal to J, so I put I here, I put I here, and EK. So, this is a vector. Okay, because there is only one unit vector now. I mean, that is what it is. Anyway, I think if you start doing some exercises, you will understand. So, let us move on. Okay. So, integral over the control surface of T dA is nothing but integral over the control surface of N dot T dA, and this can be written as divergence of T dV from the divergence theorem, which you must have studied earlier. Okay, we saw that. So, we are converting the surface integral to a volume integral. That is what we wanted to do. Okay, all of this that I have done is just to show you systematically how this surface integral can be converted to volume integral. All the other things are volume integrals, remember. So, I can just substitute everything and do what I did earlier. Okay. So, going back to the Reynolds transport theorem, I am only one step away from Navier-Stokes equation. Okay. So, you guys can breathe easy now. U dV equals control volume of rho g plus divergence of T dV. Earlier all these were volume integrals, only this was the surface integral. I have converted the surface integral to a volume integral in terms of capital T now. Okay. And since this implies, since the control volume is arbitrary in the above, the equation should be valid for any small CV, okay, or volume element. Therefore, it should be valid at every point. You take any point, this has to be valid. So, then I conclude that d by dt of rho u plus divergence of rho u equals rho g plus divergence of T. Okay. This is your Navier-Stokes equation. Maybe a very complicated way, because one way which people normally do is they do a shell balance and then look at it, but I don't want to do shell balance. We want to do it this way. But you should get the same result at the end of the day. Now, the T is written as minus Pi plus tau. P is the pressure and tau is the stress tensor. This is a tensor. Remember, this is a tensor. This is also a tensor. Okay, this is and so when I substitute this, okay, the T is written as this. This is the pressure, and this is the stress tensor. What I want to do is talk about the I need to do divergence of T, right? Divergence of T, and substitute it here. I should get divergence of minus Pi plus divergence of tau. Okay, I am substituting for capital T. What is I? I is the identity matrix which has 1 along the diagonals and 0 everywhere else. Okay. So, basically I is the which is basically 1 0 0 0 1 0 0 0 1. So, the only term which contributes in I are the diagonal terms, and in the diagonal I is equal to j, right. This is 1 1, this 2 2, this 3 3, all the others are 0. So, I can write, so if I want to calculate this particular quantity here, I am going to write, how do I calculate divergence of Pi? Forget the negative sign, negative can be pulled out. How would you calculate this? The usual method that we had, the del operator is d by dxi of Ei, okay, that is a del operator, is a vector, okay, and dotted with gradient Pi is P, I am going to write this as Ej, Ej, because the P has contributions only along the diagonal. So, I am not going to write Ei Ej, because for Ei I not equal to j, the elements are 0, okay. So, what does this simplify to? This simplifies to, when I take the dot product, I must be equal to j. So, I get dp by dxi, I must be equal to j Ei. Okay, there is a negative sign which I threw out, but remember there is a negative sign here. Okay. So, when you write the Navier-Stokes equation, this is actually a vectorial equation, 3 components x, y and z, or 1, 2 and 3. So, when you write in the direction 1, when you write in the direction x, you will get minus dp by dx1 minus dp by dx, that is the term which comes, okay. So, I mean you have to get comfortable with moving from vector notation to scalar equations by doing the components. So, I am just trying to show you how to do that, okay. So, you have this. So, this gives you, this gives the dp by dx, dp by dy dP by dz in the Navier-Stokes equation. Okay. So, that is a logical way of doing this. I mean, it is not that we are arbitrarily doing stuff. So, mathematics is a very clear subject. So, you need to understand the math that you are doing. So, I am just telling you why did I take EJ, because I contributes only when along the diagonal, and I get this. One thing which we want to do is realize that the equation of continuity is a single equation. Okay, so what are we have now? We have one equation of continuity and three equations of momentum or Navier-Stokes. Why 3? Because I have 3 directions. I have to write it in 3 directions. It is a vectorial equation. I have to write it for every component. So, totally 4 equations. And what are the variables that I am trying to find out? There are the 3 velocity components, and let us keep life simple. We have incompressible liquids and properties are constant. Okay. The 3 velocity components and the pressure. Okay. So, I have 4 equations and 4 unknowns. So, I have 4 unknowns are the 3 velocity components and pressure. But there is a small issue here in the sense that I have, in doing all of this, there is one more tau which has come up. This tau, the stress tensor which has come, and that is an additional variable now. So, basically in the process of deriving the Navier-Stokes equations, I have gotten one more term, and what I want to do is I want to close this whole thing. I do not want to keep adding more and more unknowns. Okay. So, basically tau is expressed in terms of velocity gradient for a Newtonian fluid tau is written as mu. This, remember, is a tensor, okay, and there are 9 components. This is written as gradient of V plus gradient of V transpose. Okay. The reason why we say gradient of V plus gradient of V transpose is because the stress tensor has to be symmetric. That matrix, if you look at the stress tensor as a matrix, this matrix has to be symmetric. Okay. This tau has to be symmetric. If I write only gradient of V, I am not guaranteed that it is going to be symmetric, okay, mathematically, if you want to look at it. So, remember A plus A transpose. What is the transpose of this? It is A transpose plus A, which is the same as A plus A transpose. Okay, I am just doing linear algebra. So, if I have A plus A transpose, but take the transpose of that, I get A transpose plus A, and because your matrices can be added, I get A plus A transpose. That means A plus A transpose is symmetric. Okay. So, one of the things that we are doing is trying to make this symmetric, and that is how it is defined. So, divergence of tau is nothing but divergence of gradient of V plus gradient of V transpose, and I am just going to tell you that this is equal to del square V. Okay. But I want you to do this. I want you to prove then divergence of del V plus del V transpose is equal to del square V. Okay. And how can you go about proving it? By doing the usual thing, write this in terms of EI, EJ, write that in terms of EJ, EK, whatever it is, do the dot product. I will only say one thing here, gradient of V, so show this, okay. I am not going to do this. Gradient of V is written as d by dxi EI dj EJ, okay, and this is written as d by dxi of Vj EI EJ. What will be gradient of V transpose? EI, EJ, ij element or 1, 2 element will be the same as, will now be the 2, 1 element, okay, the 2, 1 element. So, this will be dVi by dxj of EI, EJ. Is this clear? Because I mean, I am doing the transpose, right. So, whatever was in the ijth position, let us take 1, 2. In 1, 2 it is dV2 by dV1. There will now be in the 2, 1 position, okay. And I am just flipping the index here. So, same element, I get the other same position, I get the other element. So, I want you to think about this, okay. After you do this, you can substitute this back here, and you will not immediately get del square Vi. When you do it, you will get actually 6 terms, okay. When you substitute this, you will get about 6 terms, and you have to use the equation of continuity to show that 3 of them can be 0 and only 3 remain. The 3 which remain are the del square Vi. Okay, I have told you how to do it, I am not doing it. So, it turns out that I missed the mu here, so I need to put the mu here, okay. There is a mu, del dot tau is mu del square V, because I mean I can keep doing it on the board again and again, it does not matter unless you do it for yourself here. But the idea is you evaluate it, you will get a bunch of terms. From equation of continuity, 3 of the terms will be 0, only 3 will remain, that 3 will be your del square Vi, okay. So, once you can do this, then it is fine. I think we are now in a position. So, I do not think I want to do more theorems at this point of time, maybe later, but we will try and solve 1 or 2 problems tomorrow, okay. Thank you.